Yesterday we were looking at part 2 of that section, which dealt exclusively with solving logarithmic equations. And there's, are there bound to be exceptions to everything that I ever tell you? Definitely. But in general, you're looking at 2 different strategies here if you have equations that have logarithmic quantities in them. One of the situations is for you to somehow arrange the equation so you have log base b of something is equal to log base b of some other thing. It doesn't matter what those things look like. One of the things could just be x, the other one could just be a number. One could be a quadratic expression, the other could be a linear expression. It doesn't matter, because even though I write log base b of something equals log base b of some other thing, since those 2 logarithms are equal, the arguments must be equal. So what you do here is you drop the logarithmic function of both of those arguments. It's not like you're dividing both sides by log base b. That you can't divide by log base b. Log base b is an operation. That's like saying I'm going to divide by the square root symbol. You can't do that. But what you end up with is an equation which in most situations no longer has logarithms. And that equation you get could be trigonometric, it could be exponential, it could be quadratic or cubic or quartic or linear. It could be, well, whatever it turns out to be. So that's one of the options. It's not always possible to get a single logarithm equal to a single logarithm, and the reason why it's not always possible is sometimes you have pieces of the original equation that don't even have logarithms in them. In that case, your option is to arrange your equation so you have log base b as a single logarithm of something equals some other thing which is not a logarithm. And where do you go from here? You can't just drop the logarithms because there is no logarithm on the right-hand side, but what you can do is write this into exponential form, at which point in time you no longer have logarithms and now you're solving an exponential equation, which, there's other paths you can take at this point in time. Maybe you can write both sides as a common base. Maybe you can't. So that's a quick summary of what we did yesterday. Can you take a minute and look over your work and see if you have any questions? Good morning. Go ahead, Liam. Did you say 9? Certainly. So we have an equation. I'm going to rewrite it. It's 1/3 base 10 logarithm of the square root of x plus the base 10 logarithm of x cubed. And again, it's not wrong if you don't put the brackets, but I am going to get in the habit of always putting the brackets for arguments for logarithms, and I think you should too. I think it is important, even though diploma exams and math type, which is the program we use to type stuff up for exams and your textbook, they all generally don't have brackets. This is equal to n log x. So in a very general sense, Liam, this equation contains logarithms everywhere. And that means our goal is not going to be to get a single logarithm equals to a non-logarithm, because everything is a logarithm. Our goal is to get a single logarithm equal to a single logarithm. And I can pack these together. The first thing I'm going to do, and you could certainly do a couple of things at once, as long as you're willing to take a risk of making a mistake from time to time. Because if you do more in one step, then you're more likely to make a mistake. I'm just going to rewrite that root x as x to the half. This is plus log, and it's a base 10 logarithm. I don't know that that really matters because everything is a logarithm, but I'm just pointing out it is a base 10 logarithm, and this is n log x. You could certainly have moved that n up top. You could certainly have moved that n up top in the second line, but I didn't for some reason. We have to move the exponents up top, the coefficients up top as exponents of the argument, because our goal is to get a single log equals to a single log. You'll notice that when I gave you this kind of general idea here of a single log equals a single log, that the coefficient of both of these terms is the same, is 1. I mean, I suppose if the coefficient is 2 on each, you could divide it out, but we don't want coefficients in front. So getting back to this question, now what we can do is move this coefficient of a third up top as an exponent due to the power rule, and we're going to have log of, this gets a little bit clunky, but we're going to have x to the half to the third as an entire quantity. And I have no problem with you just writing x to the sixth at that point in time. And I think you're pretty much seeing where this is going. This is plus log of x cubed. This is equal to log of x to the n. So if we pack these two logarithms together on the left as a single logarithm using the product rule, which refers to the product of the argument, not the product of the logs, you're going to get a single log of x to the sixth, because when we have x to the half to the third, that's what we call a power of a power, and you multiply the exponents. 1/2 times 1/3 is 1/6, multiplied by x cubed. I'll be honest, I think these small sets of brackets are not necessary. What's important is the big set of brackets. And you know where this is going from here, I'm sure. This is log of x to the n. Now we have a product of two bases that are the same. This has nothing to do with logarithms. This is all about what you call the product rule in grade 9 and 10, where you add the exponents if you multiply the bases. So this becomes log. It's a base 10 logarithm, but again, I don't think it really matters as long as the base is the same on both sides. We have to add 3 and a sixth. You know, at this point in time, if you're so focused on logarithms, you can just use your calculator. You can convert 3 to 18 over 6 and add 1/6 and get 19 over 6. Anyway, in the end, you can see that n has to be 19 over 6. If the logarithms are equal, then the arguments, which are the things we're taking the logarithm, must be equal. This is interesting. To go from here to here, we're saying since the logarithms are the same, the arguments must be the same. And then to actually get an answer here, you're saying since the bases are the same of this exponential equation, the arguments of these must be the same. Anyway, we get the answer. Is that okay? Other questions? Go ahead, Jason.
Page 36, question 2.
Okay, so determine the value of x and y if, and I'm just going to stop there. At this level, anytime you have a question which begins with determine the value of two things, it's most likely going to be the case that you have to solve a system of equations. So how do we get a system of equations here? Well, we have a system of equations. It's right there. There's one equation that relates x and y and another equation that relates x and y. The only thing we have to do to turn this into a grade 10 question is to figure out what log base 3 of 243 is. And I don't think, like, if you have to go to your calculator, I can't stop you from going to your calculator on an exam. But you should be thinking to yourself, and you probably will want to use a calculator here for log base 3 of 243, but my point is, I don't want you to use the change of base formula to figure out what it is. I want you to say to yourself, to what do you raise 3 to get 243? And the thing you try on your calculator is like 3 to the 3, 3 to the 4, 3 to the 5, and I believe it's going to be 3 to the 5. So log base 3, I'll rewrite this, log base 3 of 243, and strangely enough, we really don't need the brackets at all there. You know, equals 2x plus y, and log base 2 of 64 equals x minus y. This first equation, equation 1, becomes, did I say 5 is 3 to the 5, 243? I want to pause there. If this were a little piddly 2-mark written response question on a diploma exam, I don't think it would be worth 3. You'll see why the rest of it becomes very simple in a minute. But if this were a written response, as a student, if I were a student, I'd be more comfortable writing 5 and then off on the side someplace writing log base 3 of 243 equals 5 because 3 to the 5 equals 243. I would actually write that down. So now we have 5 equals 2x plus y. And equation 2, well, log base 2 of 64, might have been better. I'm not really concerned about you having to erase things. It just occurred to me that provided that you have room, it might have been better for you to plan things out here if it were a written response and do something like this. Don't use an equal sign. Because the way I was doing it, it was equation 1, equation 2, equation 1, equation 2. It was kind of scattered a little bit. So this becomes 5 equals 2x plus y. Log base 2 of 64 is the exponent to which you raise 2 to get 64. Is that all? No, that's 6. Is that 6? Okay. So 2 raised to the 6 equals 64, so log base 2 of 64 is 6. And essentially right now what we've turned this into is a fairly low-level Math 10 system of equations because it's already lined up for you. If you add these two equations, the y's cancel. I'm not really happy that we're getting 11 thirds for x. Usually we would get whole numbers or integers, but is that in fact going to be? Okay, so sometimes it's not as simple as just a integer. We get x equals 11 over 3. Now at this point in time, we've found one of our unknowns. We can go to either of these equations to find y. You probably might want to use the top equation because then you're not dealing with negative y's. Really doesn't matter. Y will equal 5 minus 2x, which is 11 thirds. So now you have to figure out what 5 minus 11 thirds times 2 is, 22 over 3. Negative 7 thirds. So you get y is equal to negative 7 thirds. And these are all of these questions that have been asked so far. There's only been 2. They're legitimate candidates for a written response of some kind. Is that okay, Jason? All right. Other questions? I saw somebody else's hand up somewhere. Go ahead, Julie.
On page 34,
Number 6? This guy? Okay. So it's an exponential equation. We want to determine the value of x. Just as a strategy here, as an exam writing strategy, if it were in fact a multiple choice question, would there be anything wrong with you solving it graphically? No, because that shows an understanding on some level of how to get an answer. And what we could do, so I'm going to do this graphically and then I'll do it algebraically, is we could graph y equals 21, which of course is going to be a horizontal line at y equals 21, so we'll have to adjust our window settings appropriately. And I'm also going to graph y equals 6 raised to the 3x. Now if I do this, that's wrong. I want to point this out because if you enter 6 raised to the 3x, now you probably have a TI-84. Do you have your calculator set up so that it actually goes into the exponent? You don't. So if you do, that's not a problem because the x will appear as part of the exponent unless you use the right arrow to get out. But for you and I that prefer that other mode, what your calculator sees is this. There's a times in here. Your calculator says, well, there's a multiplication sign there, even though you didn't type it. So you're telling the calculator to take 6 to the 3 and then multiply that by x, but that's not what we want. So what you do need to do here when you enter 6 raised to the 3x is you need a set of brackets around the 3x. Now we can use some knowledge about exponential functions. 6 raised to an exponent is a growing or increasing exponential function, which in general will look like this with a horizontal asymptote on the x-axis. The fact that it's 6, everybody, and I'm using this opportunity to review some basic properties from the beginning of the unit. The fact that the base is 6 means it's going to be y. There's no word tripling, quadrupling. Y is going to be multiplied by 6 regularly, so it's going to grow really, really rapidly. The 3 in front of the x does something horizontally to the graph, but it doesn't affect the basic behavior. When you talk about y equals 21, we know that it's a horizontal line at y equals 21. So when we set up the window settings here, if we're confident enough in what I've drawn, like you understand what these graphs look like, then you shouldn't really need negative numbers. You know that they're going to intersect someplace to the right of the y-axis. So I'm going to go up to 15. I literally, Julie, I really don't know where it's going to be. I'm just saying let's go up to 15 first. I do have to go up to at least 21, so I'm going to go up to 25. So there's y equals 21. Okay, I didn't need to go anywhere near 15. And I don't even need to adjust my window settings now, but I would rather this picture that you're looking at look similar to what we have drawn. And I don't know, maybe 2. Yeah. So now we can find the point of intersection. Given that there's only 2 functions there, you don't need to worry about scrolling around. You just hit enter 3 times and let the calculator do its thing. So it's about 0.566. Now, how is this helpful when you don't see 0.566? Well, you can calculate all of these. And in fact, the fact that these were all base 10 logarithms in the answer tells you that it'd be pretty easy to double check these. So is log of 21 over log of 216 that number? Yes. A is the answer. Okay. Now, of course, again, this could be a written response question. And if it's a written response question, it would probably be worth 2 marks. But you would have to say to yourself that I need to take the log of both sides. And incidentally, I think you're going to agree, if you know what you're doing solving this algebraically, you can solve it in about 1/5 the time, I would think, as it would take you to poke around on your calculator to find the right window settings and all that other stuff. This allows us to write log of 21 equals 3x times log of 6 because of the power rule, which says that exponent can be written out in front as a coefficient. And that means that in order for me to get x by itself, Julie, I have to divide both sides by the 3 and the log 6. So I have to divide both sides by 3 log 6. And that's going to give me x equals log of 21 over 3 log 6. I look up there and I see, well, there is a log of 21 over something, but, is it this or is it this? Well, we can bring this 3 in front of the logarithm in the denominator back up and have 6 raised to the 3, which I hope is 216. Pretty sure it is. And you get log of 21 over log of 216. Is that okay? Okay. Other questions? Go ahead, Farhan.
Would that be necessary though in response to bring the exponent back up?
It's a good question, and the answer is no. I don't think. That being said, it's not necessary, but if you look at that and you go, oh, well, that is 6 to the 3 as an argument. In the time it takes you to process whether you should write that down or not, why not just write it down? I'm not saying if you don't, you would get it wrong. What I'm saying, and I firmly believe this, is when you do something like that, a marker sees that you really understand some other things that maybe are not necessary in the question, and they might be willing, because of that, to forgive some slight error elsewhere. Like, that's just the way it is. If I'm marking something, and I know that you guys struggle with this sometimes, basically 2 students have essentially the same mistake, and one student loses 1 mark and one student loses a half a mark. The student who loses half a mark is only losing a half a mark because everything else is so well explained. Other questions? Go ahead, Evan. 5H. So 5H is a logarithmic equation which is quadratic in nature. And again, I want to point something out about 2 terms in this equation, or 2 things in this equation. Log base 3 of x quantity squared compared to, and the 3 is not relevant to my point, compared to log base 3 of x raised to the 23. Which, Evan, when you see this, you know this is what it means, right? It's just the sloppy nature of the way people have developed notation for logarithms. Okay. But if you were to write 2 log base 3 of x here, that would be incorrect. My point is you cannot bring that 2 down in front, because that 2 is not an exponent on the argument, it's actually an exponent on the whole logarithm. But you can bring this exponent down in front and write 23 log base 3 of x. So when we do that, you're going to have 3 log base 3 of x quantity squared. We have minus 36, and then we're going to have equals 23 log base 3 of x. So we have a quadratic thing. I mean, you have 3 times something squared minus 36 equals 23 times that thing. That's quadratic. That's like having 3a squared minus 36 equals 23a. I don't know if there's anybody here who would benefit from this. I hope that everybody does not need to do what I'm going to do. But what you could do, and I'm going to put it on a separate page, is let a or some other letter equal log base 3 of x, which means the equation is going to become 3a squared minus 36. Minus 36 equals 23a, which really drives it home that it's a Math 20 problem at this point. I'm going to walk away from that and then come back to it after we're done, because I'm going to hopefully force you to not have to rely on that. Since this is quadratic, we can zero the equation and write 3 multiplied by log base 3 of x quantity squared minus 23 multiplied by log base 3 of x minus 36, don't forget equals 0. And unfortunately, so first of all, if this is factorable, it's not a simple factoring, it's a trial and error factoring. We can do the b squared minus 4ac test simply because if it's not factorable, and some of you can see if things are factorable very easily. I don't know how you guys do that sometimes. But I can't do that without looking at b squared minus 4ac. So if this is not factorable, I don't want to be wasting my time with trial and error and getting frustrated because it's not factorable. I want to know if it's factorable or not. I can't do that in my head. So we're going to do b squared minus 4ac. Negative 23 squared, you would need the negative in brackets. I personally wouldn't even put the negative in because when you square a negative, it becomes positive. Minus 4 times 3 times negative 36. That looks suspiciously like a perfect square. 31 squared. So because this is 961, which is a perfect square, it's factorable. It's funny, I didn't even look to see if I could factor a 3 out first, but I can't. This won't be too bad. It will have to be 3 times the logarithm of x, log base 3 of x, and 1 times the log base 3 of x. I'm going to need numbers that multiply to give 36. Now, listen carefully. I can't choose 6 and 6. I would never choose 6 and 6 here, because if I choose 6 and 6, then I paint myself into a corner where I have to put a 6 over here. But then in that binomial that I've created, there's a common factor of 3, and there was no common factor of 3 in the whole thing. So it can't be 6 and 6. Could it be 1 and 36? I guess it could be, but I don't think you would try numbers that are that far apart first. So it still wouldn't work because 6 times 6 is out. Thank you for that. 2 times 12 is not 36. 3 times 12 is 36, which is out because there's a common factor of 3 no matter what we do. You're not going to try 1 and 36. It's going to be 9 and 4. But if it's 9 and 4, sorry about that, I couldn't do my times table this morning. If it's 9 and 4, the 9 cannot go with the 3 log base 3 of x because we would create a common factor of 3. So it better be 9 here and 4 there. There we go. Negative 27 for my outer. It will be negative 27 log base 3 of x. And my inner will be 4 log base 3 of x. So there we go. So now we're ready to solve this equation. And don't forget, Evan, this is equal to 0. And now what you're going to do is set each of those logarithms equal to 0. So we will have 3 log base 3 of x plus 4 equals 0. We're going to have log base 3 of x minus 9 equals 0. To get x by itself, what we have to do is rearrange the logarithm to get the log base 3 of x by itself, and then write it in exponential form. So for example, this second equation that comes out of the quadratic factors will be log base 3 of x equals 9, which means x equals 3 to the 9. I don't think it's really important that we figure out what 3 to the 9 is. If you want to, you can. I suspect in an exam it would just be 3 to the 9 would be acceptable. The other one requires a little bit more legwork to get the logarithm by itself. You have to subtract 4 first, then divide by the coefficient of 3. So you're going to get x equals 3 to the negative 4/3, or 1 over 3 to the 4/3. And again, is that how they have the answers? They don't have decimals or... Well, they put them in decimals. Okay. That's a, you know what, everybody? That's a good 3-mark written response question. I suspect, and I've already told you this, that on the diploma exam, somewhere on the written part will be solving exponential and logarithmic equations. By the way, we're not done yet. I got to check something. And I often see one written response on this area of study where you have a 2-mark question and a 3-mark question, and the 2-mark question is an exponential equation like the one Julie asked about. 21 equals 6 to the 3x, or something along those lines, where you have to take the log of both sides. And then the other question, whether it's 2 or 3, depends on the structure, would be logarithmic. I think this is a good logarithmic 3-mark equation question. I forgot, and I don't think we've addressed this today, you have to always be looking at whether the solutions you get are extraneous or not. But since both of these numbers that we get are positive numbers, 3 to the negative 4/3 is still a positive number because it's positive 3 raised to something. And the argument is x for both of these. You're going to end up taking a logarithm of a positive number, which means it's valid. Now, if it's a written response, I think you should say that you've done that. I don't think it's good for you to just say in your head, oh, well, they're positive, so there aren't any extraneous roots, I'm going to move on. I think you should probably say, since each of these solutions leads to only positive arguments in the equation, they are valid solutions. Yeah.
So we don't need to verify the roots?
I don't think so, no. No, I don't think so. And, you know, as we get closer and closer to the diploma exam, although it's only worth a piddly 10%, you have to understand that you're going to have 3 written response questions on that exam. And I do understand that you have 6 hours, but like it's a 3-hour exam, but they double the time. But I don't know about you. I don't want to be writing an exam for 6 hours. That's a little corner of hell in my mind. To be sitting there for 6 hours doing the same thing, that's tough. But you have 3 written response questions. You have to be able to move on. You can't spend, I don't think you can spend an hour on a question. Anyway, other questions? Go ahead, Andrea. 4H. And then the question becomes, I think I'm back, and then the question becomes, so what? What now? Well, what this equation is, I'm going to rewrite it over here. 4 equals x over x plus, I keep wanting to say plus, x minus 3 to the half is a rational equation because you have x's in the denominator. It is also a radical equation because x minus 3 to the half is the square root of x minus 3. So what this equation is a whole jumble of different types of equations. It's rational because there's a fraction involving x in the denominator. It's radical because there's a square root of a variable. When you look at the bigger picture, it's rational, and inside of the rational expression is a radical. When you solve a rational expression, or a rational equation rather, you learned last year that your first step is to multiply everything by the lowest common denominator to eliminate any denominators. That takes a rational equation and turns it into a non-rational equation, which now you have a fighting chance of solving. I do understand, everybody here, that you can cross-multiply because 4 is 4 over 1. But cross-multiplication is a tool that's just very specific to this type of rational expression or equation, where you have one fraction equal another. I think it's better to say I'm going to multiply both sides of the equation by the denominator so that I can cancel the denominator and be left with 4 times root x minus 3 equals x. Now, and by the way, a rational equation and a radical equation are both taught to you in grade 11 math. Okay, this is all about grade 11 math. When you have a radical equation, which is what we're looking at now, your goal is to isolate the radical and square both sides to eliminate the radical. So we're taking this equation that's in brown at the top of your screen, which contains fractions and radicals. We've gotten rid of the fractions, making it easier. Now we're going to get rid of the radicals. I don't think you have to divide both sides by 4 before you square it. Well, I know you don't, but my suggestion is don't do it. Just do it from here. When I square a product, I have to square each of the factors. So I have to square the 4 to get 16. I have to square the root of x minus 3, which gives me x minus 3. And then on the other side, I'm squaring x, which gives me x squared. I see that it's quadratic, which means I have to zero the equation. At the same time here, Andrea, I'm going to zero the equation by moving everything to the right side. At the same time, I'm going to expand that 16 times x minus 3. 16 times x is 16x, and I'm subtracting it. 16 times negative 3 is negative 48, but then I would have to add it. Are there two numbers? Because the coefficient of the first term is 1, I don't think it's necessary for us to delve into b squared minus 4ac. We can just ask ourselves, can we find two numbers that multiply to give 48 and add to give negative 16? Negative 4 and negative 12. So this in factored form is x minus 4, x minus 12, which means x equals 4 and x equals 12. This is a little tricky now. When you check for extraneous roots, remember that you want to go back to the original equation. So, what did I say? 4 and 12? Is that what I wrote? Yep. When I put 4 in to the left and the right side, both of the arguments will be positive. When I put 12 in, both of the arguments will be positive. So 4 and 12 are both legitimate solutions. Other questions? No? I'm going to hand out a review package that I just want to go through quickly with you, and then we can practice some review today. And remember, we're reviewing today, we're reviewing tomorrow, we're reviewing Monday. So your exam is Tuesday of next week. So this is a review of exponential and logarithmic functions. We started off by looking at basic exponential functions, and there were two basic exponential functions that we looked at. They were all of the form y equals some base to the x, but the first one that we looked at was where the base was greater than 1. And the things that we learned were that the y-intercept of that function was 1. There's a horizontal asymptote on the x-axis, which I'm not showing here, but that's okay. You know it's there. And it's an increasing exponential function. It's a growing exponential function. Whenever you talk about whether an exponential function is increasing or decreasing, you're talking about what's happening to y as you go left to right. You are expected to be able to take that function and transform it using a, b, h, and k. And this is why I prefer to use the base c when I talk about this. Because if I use b for a base, then we're going to have b for a base and b for a horizontal stretch parameter. The bottom line is if I give you an exponential function that's already been a transform exponential function, and I ask you for the properties of it, the only way you can answer that is if you know what the properties of this original exponential function are. So knowing what this looks like and knowing the fact that y equals 0 is a horizontal asymptote leads you to the conclusion that for the transform function y equals k would be a horizontal asymptote. Decreasing exponential functions. So again, we are dealing with the same basic exponential function, and you're still expected to know about the properties of a transformation of it, except this time the base is between 0 and 1. And that, by the way, explains to you in a review form that the base of an exponential function cannot be 0, cannot be 1, and it cannot be negative. But the result is a decreasing exponential function. Exponential growth and decay follow that pattern where you have the graph either increasing or decreasing, and this is really just the two graphs that I've looked at already, but they are transformed in a different way. And my suggestion to you is when you use this formula in the red box that's on your formula sheet, you do not try to interpret its meaning by talking about transformations. Don't do that. It's a memory thing. Y is the quantity that's growing or declining. A is the initial value of the property, whatever it is. B is the factor by which things are changing. T is the variable time. So T and Y are variables on a graph. And P is the period of time it takes to happen. So for example, if you're dealing with a situation where half-life is 34 years, that means B is 0.5 because things are being cut in half regularly. It means that T, or P rather, is 34 years. That's the length of time it takes to happen. If you have a population growing by 4% every year, since it happens every year, P is a year. Since it's growing by 4%, B, the factor by which the population is being regularly multiplied by, B is 1.04. I hope everybody understands how to go from an increase of 4% to a B value of 1.04. It's 104%. If the value of something is declining by 12% every 6 months, well, that means that it's losing 12%, which means you get to keep 88%, because I think 100 minus 12 is 88. which means b is 0.88. And p is the length of time it takes to decline by 12%. Now, just a second. Would there be anything wrong with you using p equals 0.5? No. But that would mean that your y value that you would calculate would be in years. Is there anything wrong with you using the number 6 for p? No. It just means that your y value would be calculating a number of months. The other thing is, if you use 6 for p, then you better make sure that whatever you put in for t is in months. You have to use consistent units. You know, just one final example here. If you have 8% interest that's compounded quarterly, b is 1.02. Why is b only 102% and not 108%? Because that 8% is compounded quarterly, which means you get a quarter of it at a time. And if you only get a quarter of it at a time, then that means it's spread out over a full year, which means that the period is only 0.25 of a year, or 3 months. So there's a logarithmic function y equals 3 to the x, or the exponential function is y equals 3 to the x. The corresponding logarithmic function is y equals log base 3 of x. A logarithmic function is the inverse of an exponential function. So these two things that I'm going to highlight are not the same thing. They are inverses of each other. The thing that I've highlighted in green is this function. The thing that I've highlighted in blue is this function. However, the thing that I've highlighted in green, which is x equals 3 to the y, written as y equals, can be written as y equals log base 3 of x. So these two things on the bottom are the same. And we don't typically walk around saying, oh, the function is x equals 3 to the y. We would much rather say the function is y equals log base 3 of x. If you have a logarithmic function with a base greater than 1, like, for example, I think the one that I printed out for you is log base 2 of x. Is that right? Just make sure. Then this is what the graph looks like because, and I don't want you to necessarily muddy up your diagram, but because this is the inverse of y equals 2 raised to the x. And 2 raised to the x would look like that. So the inverse is a reflection in the line y equals x. It makes sense that that's what it looks like. Just as you're expected to know what transformations of exponential functions look like based on your knowledge of the basic exponential function, you're expected to have this basic knowledge of this graph you're looking at so that you can tell me about any transformation of that function. So if I give you as an example, y equals negative 2 log base 3 of 2x minus 4 plus 8, you should be able to tell me, for example, the domain and range of that, where the asymptote is. The asymptote, by the way, would be at x equals 2 for this function, because you have as an argument here 2 times x minus 2, which means that the h parameter, which is the horizontal shift, is 2. The vertical asymptote on the original graph is here. So that's why you would know where it is on the transformed graph. If the base is between 0 and 1, and I don't usually see this on exams, but if the base is between 0 and 1, this is what the logarithmic function looks like. Because this, which I really hope on your printout it says y equals log base a half of x. It does. This is the inverse of y equals 1/2 to the x. And 1/2 to the x looks like that. So when you reflect that graph across the line y equals x to get the logarithmic function, which is the inverse of that exponential function, it has to take on that shape. But if you know that's what a logarithmic function looks like when the base is between 0 and 1, then again, you should be able to determine the properties of any transformation of that exponential function, or logarithmic function, rather. The laws of logarithms become a very significant aspect of this unit in terms of evaluation and exams. You need to know how to use properly the three main laws of logarithms, which is the law that we call the product law, which says the logarithm of a product is equal to the sum of the logarithms. The quotient law, which says the logarithm of a quotient is equal to the difference of the individual logarithms. With the quotient law, the order in which the individual logarithms are subtracted is the same as the order in which the arguments are divided in the single log. So if m is on the top, you're going to take log m minus log n. Go ahead, Liam.
For the written response, if you don't remember the names, can you just like show?
Yeah, this is not like trigonometry where you would be expected to name them. If that's what you were asking. Yeah, you don't have to. In fact, you know what? I would go so far as to say you don't even have to write them down. If you are doing some work on a written response and at some point you have that, and in your next line you write this, I don't think you need to explain that in any way. The change of base formula. The change of base formula becomes important because sometimes you need to change the base of something, either to evaluate it on your calculator for those of us that don't have the log base function. And I forget, there was somebody here whose operating system we wanted to update. Was it you? Okay, we'll see if we can take care of that today, to include that log base function. But you may also want to use the change of base formula for other reasons. Maybe, I mean, this is really kind of cheap, I think, on an exam. But I have seen cases where if you solve an equation, maybe an exponential equation, by taking the logarithm of both sides, you end up with, as an answer, maybe this. Like, let's say you're solving some kind of equation and you get that for an answer. And it's multiple choice. And that's not there. But what is there is log of 6 over log of 3. Well, you should recognize that if you apply the change of base formula to log base 3 of x, you'll get log of 6 over log of 3 in base 10 logarithm. It could be that you have this question where, I apologize because I can't really think of a specific example that would lead you to this, but you do everything by the books and you get that, and it's a numerical response question. And it says the answer is log of A over log of B. You need to recognize that log base 3 of 6 is the same as log of 6 over log of 3. And again, when I say log of 6 over log of 3, these are base 10 logarithms. briefly, there's a shortcut here that if you have so many logarithms, like you have 5 or 6 logarithms all in a row, the rule is if you have a positive logarithm, the argument that's in that positive logarithm will go on the top of the argument when you consolidate all of the logarithms and bring them together. And the argument that's in a negative logarithm will always go on the bottom. You know, it occurs to me, I don't really have in this review package, I think I didn't put it here because it's just obvious, I hope. But, you know, I hope you need no prodding in understanding what the meaning of a logarithm is. Right? So, for example, we use this all the time. If I said to you, what does log base 3 of 6 mean? Well, it's going to be a number someplace between 1 and 2. Because it's the exponent to which you raise 3 to get 6. So that goes back to the log base 3 of 243 I think we had today. You should be able to understand that it's 5. You shouldn't need to change a base formula to evaluate a logarithm. And finally, the very last thing is you need to know how to solve equations. If it's an exponential equation, there's 2 things that you could possibly encounter. One is that you can write things as a common base. And I will warn you right now, everybody, that if I give you on an exam or you see on a diploma exam something like, we'll make it a little more interesting, that, and you're asked to solve that, could you take the log of both sides? Yes, you could. You could always do that. But taking the logarithm of both sides of an exponential equation to solve it, when you could instead use a common base, is a mistake. It's going to get too complicated. The idea here is that you write this as 3 squared. This is raised to the 2x minus 5. You write the 3 as a root as 3 to the half. You write the 81 as 3 to the 4. And then you bring together all of the exponents on each side. So, for example, we're going to have 3 to the 2 times 2x minus 5, because that's what you do with the power of a power. Here you're going to have 3 to the half plus 4x. The power of a power for 3 to the 4 to the x is 3 to the 4x. But then you're multiplying a common base, so you add the exponents. Then what you can do is say 2 times 2x minus 5 is equal to 1/2 plus 4x. I would personally multiply both sides by 2 at some point in time to eliminate that half. But anyway, you're off and running. If you cannot use a common base, then that's the stuff we learned 2 days ago, where you have to take the logarithms of both sides in order to bring the exponents down. For solving logarithmic equations, which is what we reviewed today from yesterday, either get a single log equals a single log and drop the logs, or get a single log equals a non-log and write it in exponential form. In either case, if your original equation contains logarithms, you must always check for extraneous solutions. And that's the review. So I'm now going to hand out the review package that has multiple choice numerical response, all that stuff on it. I've really broken this one down into sections. So there's a section called graphs of exponential and logarithmic functions. There's a section called applications of growth and decay, etc., etc., etc. There's also at the end of your unit, like boatloads of extra practice. Okay, so I'm going to hand that out, and then we will get to work on it. I know there's not a lot of time left, but this is one of the reasons why I've left 2 extra days. So tomorrow we're going to be going over as many questions as you want and working on as much math as we can, and we're going to repeat that process on Monday.